What's up, folks? How we doing? Getting into this chapter 4. We're starting a new section. All right, I'm rocking out a little bit this morning here. This band is called Bailiff. They're really good. Okay, let's get it going here, folks. Okay, I could jam out all day like you know I can. So, I've got the chapter 4 learning goals up here. So this is going to be a really important chapter. We're going to start seeing ourselves really get into the meat of chemistry now. Okay, so in this first lecture on chapter 4, I'm going to cover just these first 3 learning goals. So we're going to talk about understanding the components of a solution. So that's what we're getting into now is solution chemistry. So we're going to talk about solutes, solvents, electrolytes, precipitates, supernatants, all this stuff, okay? And I want you to understand what that stuff is. So we're going to get into calculating solution composition. And there's going to be several units of solution composition we get into, such as molarity, grams per liter, grams per milliliter, or even part per million. So this is a way of calculating concentration. These are all different ways of expressing a concentration. And then finally, the last thing I'll talk about in this lecture is know how to perform a dilution calculation. So in other words, if we have a highly concentrated solution and we want to dilute it, we want to make it less concentrated, I want you to know how to do those calculations as well as what's going on in a dilution. Okay, so let's put this away. And here we go. Let's get this started. Yes. Okay. So what we have here is a picture of water dissolving salt, as you can see right there. Ooh, let's make my line a little bit thicker. Yeah, there we go. Okay. Water dissolving salt. And so I'm going to walk you through. There's a lot of cartoon representations of our molecules on here. So here we have the H2O molecule, the water molecule, okay? And as it turns out, this molecule has this bent geometry, okay? We're gonna learn this, why it has this bent geometry as we progress. But for now, I'll just tell you that it's got this bent geometry. There's 105 degrees between those bond angles, okay? Or the bond angle is 105 degrees. So now you notice that I have this thing here, this 2, and that's a lowercase delta with a negative sign. So this means partial charge, okay? So we know water is a covalent molecule. It's not ionic. It is covalent, meaning it shares electrons between neighbors. However, as it turns out, not all atoms share equally, okay? And oxygen just so happens to be a bully for electrons. So in this sharing, okay, so we note the oxygen has a partial negative charge that's roughly like, let's call it 2 minus. That's what that corresponds to. It's not 2 minus. We know oxygen atom by itself or an oxygen ion is 2 minus, but all the same, it's negative. That's what we can conclude. It's partially negative. And we also notice that the charge on each hydrogen is partially positive. This makes water a fantastic solvent, okay? Because it has these partial charges, negative on one side and positive on the other side. It is really good at dissolving material. And some folks even go on to call water God's solvent, okay? Because it can dissolve a lot of things. So what does it mean to dissolve something, okay? Well, here I have a nice chunk of some salt, some sodium chloride, NaCl. The sodium plus are represented by those gray circles, right? The cations. And the Cl minus are represented by these green circles, the anions, okay? And as water starts to dissolve this, you notice what can happen. The partially positive side of the water molecule can orient itself near the anions, and the partially negative portion of water can orient itself near the cations, okay? And so as this chunk of salt starts to get dissolved, imagine putting a chunk of salt in your cup of water, right? You wouldn't be able to see this happening. You'd have to shrink yourself down to the size of a molecule. But if you could, you would note that as it's getting put into this water, I'm going to put H2O liquid, okay, on the side of the arrow, the ions become a part of the solution, okay? And those ions are surrounded by the water molecule. In the case of the anions, look, those positive hydrogens are like kind of shepherding the anion, and then those negative oxygens are kind of shepherding those cations into the solution. Okay, so now let's move forward and talk about a little bit of these definitions. Okay, so in this situation, so where I've got NaCl solid, okay, a solid chunk of sodium chloride being dissolved, we can express now that the anions have been dissolved, the ions I should just say, and we can express that they've been dissolved with this AQ, aqueous, okay? That AQ means aqueous. And that aqueous implies that these ions are in water. Specifically, they are in water. And furthermore, I want to comment that when we have an anion like this, Na plus, or excuse me, a cation, or an anion, these ions, okay? These ions don't really exist as charged species unless they are in a solution. Now, that's certainly not the total truth, okay? We can have gas phase ions. That's called a plasma. When you have a gas that's predominantly made up of ions. However, that's pretty rare in the grand scheme of things, okay? So almost always in nature, when you have something charged, it is in an aqueous solution, okay? It is very difficult to have something charged, to have an ion, unless it is dissolved in water, okay? So I want you to start wrapping your head around that when I see a charge on an ion, there is a very likely, strong probability that it is in an aqueous solution, okay? So now, in this situation here, we would call NaCl the solute. We would call the liquid water the solvent. It is dissolving the solute. And when this happens, when we use water to dissolve sodium chloride, for example, it makes an electrolyte. Okay, so sodium chloride is an electrolyte. So the Na plus and the Cl minus, it is a substance that when dissolved in water can produce a solution that will conduct electricity. I'm going to try to rig up a demo of this for you. And if I can't rig up a demo, then I'll comment on some YouTube videos, okay? But this is for real. When you have a salty water solution, it can, in fact, conduct electricity. And what I hope to be able to show you in a demo, perhaps in my garage or something like this, that a salty water solution, a concentrated salty water solution, is actually a better conductor than like a copper wire itself, like a wire that you plug into the wall to conduct electricity to charge your cell phone. More often than not, these salty water solutions are better conductors than the wire itself, and I hope to be able to demonstrate that to you. Okay. So solute, solvent, electrolyte. Okay. And so there was another definition that I don't have on here. Okay, or two other definitions rather, that we'll get to in time, and that's precipitate and supernatant, okay? And I'll come back to this again, but just very briefly, okay? Suppose we now have a solution, right, where not everything dissolves. So you notice in this picture here, we have here the sodium chloride solute, but now it's completely dissolved, okay? And so if it's completely dissolved, we would describe that as homogeneous, okay? So it's one consistent phase. We don't see any solid chunks in there. But suppose we had a solution now where not everything dissolved, right? So let's say not everything dissolves, okay? That can happen from time to time. We can have solutions in which our solute will completely dissolve and it makes a homogeneous solution. Or when we have this situation here where not everything dissolves, and we're going to talk about why that is in future lectures, okay? Then we would call it heterogeneous. I can't spell today. Heterogeneous, okay? And now, when we have a heterogeneous mixture, okay, so we can have a homogeneous solution, but this heterogeneous has to be a mixture, okay? Because in this heterogeneous mixture, not everything is dissolved. It hasn't made a proper solution, okay? And then now continuing along with this, in our heterogeneous mixture, the chunks, so the solids, we call the precipitate. The precipitate, okay? And the liquid above the precipitate, we call the supernatant, okay? So that's only in the case of a heterogeneous mixture. So right now I have some coffee. Coffee's good. I make my coffee with a press pot, grad student strength, as strong as I can get it. There are definitely some chunks of coffee grounds at the bottom of my coffee cup. I know that sounds gross. I don't care. I don't swallow them. It's easy. And my press pot doesn't always get them all, okay? In this example, and I would show it to you, but it's not in a clear cup, right? There it is, the black stuff, okay? The coffee grounds are the precipitate, and the rest of the liquid in my coffee is the supernatant, okay? But now, in my cup of water right here, undoubtedly, there's some dissolved ions in here, right? I have a water filter on my sink, but it's not going to filter out every last single ion. There are undoubtedly some ions in here. Probably some sodium, probably some chloride, and some other minerals that just so happen to be good for my body. This is homogeneous, okay? Let's see, I don't know, you probably can't see it. It's completely dissolved. When I look at it, it just looks like pure water, but it's not pure water. It's got some stuff in there, okay? So understand the difference between homogeneous solution and heterogeneous mixture. And then within a heterogeneous mixture, understand that the solids are the precipitate and the liquid in our heterogeneous mixture is the supernatant. In our homogeneous solution, the only thing we have is the solvent and the solute, okay? The solute would be the dissolved ions, the ions that become dissolved, and the solvent is the liquid that did the dissolving, all right? Moving forward. Oh, and then here's a, again, just another cartoon representation showing you how the positive side of these water molecules will surround the anion, and the negative side of the water molecules, the oxygen, will surround the cation. That's how it's able to make this homogeneous solution, okay? And the reason why it can conduct electricity, which again, I hope to demonstrate for you soon. It can conduct electricity because now the charges have been separated and they're no longer neutralized, okay? So in this picture, when it's a solid salt crystal cannot conduct electricity because all of these charges, positive, negative, negative. They're all neutralizing each other. They're all balancing each other. But now, once this thing is in solution, those charges have all been separated, okay? And because those charges have been separated, you can actually pass a current of electricity through them. It's very cool, okay? So moving along, so we quantify solution composition by using various forms of concentration. Okay, so how much solute is in our solution. And we do that by using molarity. And molarity is always given with a capital M. And we also use brackets to express molarity. So for example, if I were to write bracket, let's say Na plus bracket, okay, this is shorthand for the molarity of Na plus in an aqueous solution. So we want to start getting used to seeing these brackets in chemistry. These hard brackets mean molarity. Okay, so what's molarity? Molarity is the mole of solute. So how many moles of solute divided by the liters of solution. Okay, so oftentimes we might see the letter N for moles and capital V for volume of solution. Okay, so a lowercase n is often for moles, okay, and a big capital V is often the symbol for liters. So moles per liter equals big capital M. So I'm giving you several different ways. This is common in science where we have several different ways of expressing the same thing. All right. So we can do dimensional analysis or stoichiometry on our definition of molarity. So for example, suppose I take V, the liters of solution, times big capital M, the molarity. What do we get? Well, V is liters of solution, okay? So that's liters. And look, molarity is the same thing as saying mole per liter. So the liter and the liter cancel, and you're just left with moles. And specifically, that's the moles of the solute, okay? So that could be the sodium or the chloride or both, right? Okay, so if we now, on the other hand, take our mole of solute, okay, so that's I'll represent with lowercase n for our moles of solute, divided by our molarity, big capital M, okay? So that's the same thing as saying now mole times, and then look, if we divide by molarity, so we know that molarity is mole over liter. So if we divide by molarity, we flip it. It now becomes liter over mole. And the mole cancel, which just leaves us with liters, right? So up here, right, we got mole, okay? So instead of trying to remember formulas like do I take moles divided by molarity or do I take volume times molarity, just remember your dimensional analysis, okay? So for example, if something is 0.5 molar, so that's the same thing as saying that it's 0.5 moles in 1 liter, okay? So that means the same thing. And so now, in the same way with our dimensional analysis, right, in my process where I go down, up, down, up, down, up, okay? If we can recognize that I can convert, let's say, 0.5 molar into 0.5 moles over liters, now I recognize that I can flip this around just like I do with density in my dimensional analysis problems, okay? And I'll have several examples for you to work on in our discussion, all right? So moving forward, okay? So here's an example. Here's another good example, okay? So calculate the molarity of a solution prepared by dissolving 1.56 grams of gaseous HCl in enough water to make 26.8 milliliters of solution. Okay, so how do we do it? Well, we need to convert this into moles, and we need to convert this into liters, and then we divide the two results, the moles by the liters, and that gives us the molarity. Okay. So, and then the wording of this, where it says in enough water to make 26.8 mils of solution, the reason why the wording is expressed that way is because we have to consider when we measure out a volume of liquid and then we add something to it, like a solute, it could increase the volume of that liquid, right? So we have to be very careful when we're talking about the volume of our solution. Does that volume already contain the dissolved solute or does it not? And so the wording of this, in enough water to make 26.8 mils of solution, that indicates, that implies that the solute has been added. So 26.8 milliliters is the volume of our solution. Okay. So I'll start by taking the 1.56 grams of HCl, and I just want to convert that to moles, and I can do that using the molar mass. So I calculated that already. That's 36.46 grams of HCl in 1 mole. Okay, and when I do that, let's see here. I've got 1.56 divided by 36.46. Okay, and so I get with 3 significant digits, 0.0, let's call it 428 mole. Okay, and so now I've got to calculate my volume. So 26.8 mils of solution. Okay, so I know 26.8 milliliters. I want to convert it to liters. Okay, so, and I know that there's 1,000 milliliters in 1 liter. So I just moved the decimal over 3 times. So that's 0.0268 liters. And then now finally, to calculate the molarity, I'm just going to divide this by 0.0268 liters. So, and I'm going to keep, like, you know, I estimated sig figs up here, right? But look, I'm going to keep the result of my calculator. Because since this is a multiplication and a division, I can just do the sig fig rules at the end. So I wrote 0.0428, but I'm keeping all of these digits in my calculator, okay? So I'm going to say now divide by 0.0268 equals, and now that's 1.5965, 3 significant digits. So I'm going to say that that's 1.60 molar with a big capital M. So molarity describes, or molarity is moles over liters. Molar describes the solution. So we could say that this is 1.60 molar is how I would describe it. Okay. So now here's a different type of problem. Give the concentrations of each type of ion in the following solutions. 0.5 molar cobalt, that's got to be cobalt 2 nitrate. Okay, so let's break that down. So when I'm looking at that formula, I recognize that that's got to be cobalt 2 plus, and I also recognize there's 2 NO3 minuses. If you're not comfortable with breaking apart a formula into its ions like that, need to review, okay? And so now I'll show you how I can set this up like a dimensional analysis, which is kind of the long way of doing it. But then hopefully if you get comfortable with this, you're able to just kind of do this in your head really quick. So if I say 0.5 molar cobalt 2 nitrate, okay, look at this. I know in 1 mole, let's see, how do I want to do this? Yeah, I know in 1 mole of cobalt 2 nitrate, there's 1 mole of cobalt 2 plus. Okay? So 1 divided by 1 is 1. And so that means for A, it's 0.5 molar cobalt 2 plus. Okay, now what about the nitrate though? Okay, so let's do that down here. All right. So then in 0.50 molar cobalt 2 nitrate, or really I should say in 1 mole of cobalt 2 nitrate, there's 2 moles of nitrate. So then that means that it's actually 1.0 molar nitrate. So this will be confusing for some of you based on my experience, okay? So let's just think about this, right? If I start with 0.5 moles of solid cobalt 2 nitrate, so I've got some solid chunks, I've got a powder, okay? And I put that and add enough water to make 1 liter of solution. So 0.5 moles in 1 liter. So that's 0.5 molar cobalt 2 nitrate. But now, once that dissolves, the solution is going to be 0.5 molar cobalt 2 plus and 1.0 molar nitrate, because in cobalt 2 nitrate, there's 2 nitrates for every 1 cobalt. Okay, I'm going to leave this part B for you to do on your own, but I'll just say very briefly, hopefully maybe you can see this now. In 1 molar iron 3 perchlorate, there's going to be 1 molar of iron 3 and 3 moles, 3 mole per liter, or 3 molarity perchlorate. Okay, hopefully you can see that without having to go through this dimensional analysis. If not, practice makes perfect. Okay, so let's keep moving forward. So there's more than one way to express concentration. Molarity is preferred in chemistry. Okay, but here are some examples of some components in seawater as well as human serum. So in other words, like blood, you know what I mean? Okay. And notice it's expressed in grams of solute per kilogram of solution, or kilogram of solvent rather. Let me just double check that for you. Yes, so that's grams of solute per kilogram of solution. We could also express it in millimole of solute per kilogram of solution, or even just in millimolar. Okay, right? So if molarity is mole per liter, I can also have a millimolar. I know that gets really confusing, little m and big M. So, but millimolar means 1 times 10 to the minus 3 moles in 1 liter. Okay? I could have micromolar. Micromolar means 1 times 10 to the minus 6 moles in 1 liter. I could even have nanomolar, which would be 1 times 10 to the minus 9 mole in 1 liter. So recognize that we can apply our unit analysis to this concept of concentration. And that actually makes things much more useful, because look at the concentration. So in seawater, not surprising that sodium is the highest component, as well as chloride, right? Seawater is very salty, and it's mostly sodium and chloride, okay? But now when you look at things like fluoride or even strontium, look, the concentrations are tiny. Teeny, teeny, tiny. I mean, even for the strontium too, look, this is being expressed in millimolar, okay? And it's still like 0.0928 millimolar, so maybe using micromolar would be best. And then if you look at the concentration of these ions in human blood, look, it's tiny. Less than 3 times 10 minus 4 for strontium 2, okay? Or even for, let's find some other ones that we, I don't want to quite talk about this thing yet, okay? But like if we look at, I don't know, let me find a small one here besides the strontium 2. I mean, even magnesium is really small, okay? So there are other units we can use to express these concentrations, more useful units. And one of those is the part per million, okay? And so what part per million means, if you have one solute, okay, then you have 1 million of the solvent. So that's what 1 part per million means, okay? For every one of these, for every one solute you would have 1 million molecules that are the solvent. So there's some more useful ways to express this for solutions. So let's follow through this, okay? So this is a microgram per gram, okay? So a microgram is 1 times 10 to the minus 6 grams. So there's our part per million, right? Instead of saying like for every one solute particle, I have 1 million. Let me write this up over here actually. So instead of saying like what I said right here, okay, for every one solute molecule, I have 1 million solvent molecules, or excuse me, solution molecules. Really, I should say that, okay? More correct to say solution. I could also then say, well, if I have 1 microgram of solute, that's the same ratio as 1 gram per solution, okay? And so now follow through the line here. So a microgram is the same as, or rather I should say 10 to the 3 micrograms of solute is the same as 1 milligram. So this gets a little confusing, so follow through here. So 10 to the 3 micrograms is the same as 1 milligram, okay? So now that 1 milligram, look, it stays, all right? And then now let's follow the gram solution, okay? So follow this all the way here, right? 1 gram of solution. Now what I can say is in 10 to the 3 grams of solution, it's the same as 1 kilogram. So an equivalent of 1 part per million is also 1 milligram of solute per 1 kilogram of solution. And if I back up on the slide right here, we have here grams per kilogram, right? But let's find one that's roughly 1 milligram. So let me pick on this strontium right here, okay? So 0.00794 grams. I'm going to convert that to milligrams, okay? So I know in 1 gram, there's 1,000 milligrams. So that equals 7.94 milligrams. And look at the unit. It's 7.94 milligram of solute per kilogram of solution. And let's go back to this next slide here. Let's go forward. 1 milligram of solute per 1 kilogram of solution is the same as a part per million. So here we go, 7.94 milligrams of solute per 1 kilogram of solution. So this is the same thing as 7.94 ppm, part per million. And so when we look at this unit, you're going to hear me say this often, chemists are lazy. We like to express things in something that's easy to say or write. So instead of saying 0.00794 grams of solute per kilogram of solution is the concentration of strontium 2+, it's so much easier for me to just say it's 7.94 part per million. Right? That took way less space, way less time to write. All right? And we do this often in chemistry and in other forms of science. We convert units around just to make it easier for ourselves to express things. Okay, so for example, right off the bat, I can say this fluoride concentration, if I look at it right here, well, actually, I think I had that as an example. Yes, express the concentration of F minus from table 4.1 in part per million. Okay, so let's break that down again. So that's 0.00130, and that's going to be grams of F minus per kilogram of solution. All right? So we can keep the kilogram of solution. That's all good, right? I don't need to do anything there. But now I want to convert this grams of F minus into milligrams. So I can say 1 gram of F minus is the same as 1,000 milligrams. Okay. And now that gives me, move the 3, 1, 2, 3. That makes it 1.30 milligrams of F minus per kilogram. I'm going to start giving you my abbreviation for solution. I say sol apostrophe T. That's how I abbreviate solution. And so 1.3 milligram of F minus per kilogram of solution, that's the same as just saying 1.30 part per million of F minus in seawater. And that's just much easier to say. Okay. So I'm going to move forward and talk about dilutions. Okay. And this will be the last bit that I talk about in this video. Okay, so I have a picture right here, so let's follow through it. So we first start with what we call a stock solution. And a stock solution is going to be something that's very concentrated, okay? So like, for example, if you like to make orange juice using those frozen, like, you know, those little tiny frozen juice things, right? And then you put it into water and you bring up the volume of water to like a gallon or something, that would be your stock. Or like, for example, if you make some super concentrated Kool-Aid, like way too concentrated, it's way too sweet, that would be like your stock solution. So your stock solution is often provided to you by a manufacturer or some chemical company or some stock room, literally a stock room, because for those manufacturers or stock rooms or companies, it's easier to give you a more concentrated solution. But perhaps you want to use a more diluted version of that. So here's what you would do. You would extract some volume. Suppose you would extract 25 mils. Okay? You transfer it to a new container. So now you've got 25.0 mils of your stock solution. Then you would add water or whatever the other solvent was. In this case, we've only been talking about water as a solvent, but we could use alcohol as a solvent. We could use oil as a solvent, okay? There's a number of things we could use as solvents. Mostly in this class, we're just going to be talking about water, though. So now we would take this stuff. This would be our solvent, and it has to be the same solvent that was in the stock solution. And we would bring the volume all the way up. And look at this. It's saying now it's bringing the volume all the way up to 250 milliliters. So we would have diluted this stock solution by a lot. Okay, and I'll get into that quantitative amount in a moment. Okay, and so now what are the new concentrations? Or what is the new concentration? Okay, so here, so this is giving you like a run through of this. I'm going to switch over to this formula right here, the famous M1 V1 equals M2 V2. So yes, that's molarity of the stock solution times the volume of the stock solution. And now this is going to give me the new molarity of the dilute solution as well as the volume of the new dilute solution. M1 V1 equals M2 V2. And if you think about this for a moment, I'll write this up here in the lines. We know molarity is mole per liter times liters. And we also know this is molarity over liters times liters. So in other words, the liter and the liter cancels, and the liter and the liter cancels. And what's important to note about dilution, it ends up being mole equals mole. So in other words, when you make a dilution, you don't change the number of moles. You're only changing the volume, or in other words, the concentration. Okay? So for example, if we work through this example, and let's just say, suppose that this was, I'm just going to say, suppose this was 1.00 molar for our stock solution. Okay? And we do this thing where we go 225 mils of the stock solution diluted up to 250 mils of the new volume of the new dilute solution. Okay? What's going to be the new concentration? So here's how we can do this. So we've got M1V1 equals M2V2. So my M1 would be 1.00 mole per liter. So as it turns out, we don't have to make this volume into liters as long as both of these volumes on this side are in the same unit, milliliters and milliliters. Okay, so that's all good. So I'm going to actually just, instead of writing moles per liter, I'm going to just write molarity. And again, as long as both of these volumes are in the same unit, so V1 and V2, as long as they're the same unit, that's okay. It doesn't have to be liters or gallons or whatever, as long as they're both the same. All right. So V1 here was 25.0 milliliters. M2, we don't know what that is. We're trying to figure out, you know, if this was originally 1 molar and I took 25 milliliters of it and then diluted it up to 250 total milliliters, what's the new concentration? So now I know my V2 has to be 250.0 milliliters, and I can solve for M2 by doing the algebra. So I'm going to divide by 250 milliliters over this side, and I'm going to divide by 250.0 milliliters over this side. So we know all of that cancels, and look what happens to the units. The milliliter and the milliliter cancel, so I'm going to get to my molarity unit anyways. Okay? And so those of you that are good with math might have guessed this, but you can see we're diluting it by a factor of 10. Okay, so 25.0 divided by 250, okay, gives me 0.1, and times the 1 molar, yep, you guessed it, M2 is now 0.1. So 3 sig fig, 0.0 molar. Okay. So those of you that are good, that can see the kind of math in your head, you might have recognized off the bat right away, we diluted it by a factor of 2, or by a factor of 10. But now you might not always have these nice whole numbers, 10 or 2 or 5 or whatever. So this is where you want to use M1V1 equals M2V2 to calculate dilutions. Okay. And so now let's see. So here's another example problem. What volume of 16 molar sulfuric acid must be used to prepare 1.5 liters of a 0.10 molar solution? I'm just going to give you the answer, see if you can work it out. Okay? And the answer is what volume, so this I'll just tell you is our stock, the 16 molar. And now we're asking, so if I would call that M1. So what volume of this, so that's V1, that's what it's asking us for. It's asking us for V1, okay? Used to prepare 1.5 liters of a 0.1 molar sulfuric acid solution. So this 1.5 liters is going to be V2, and the 0.1 molar is going to be M2. So see if you can solve for V1. I'll tell you the answer is 9.4 milliliters. Okay, see if you can come up to that answer. I'm going to move forward. And the last thing that I'm going to talk about with respect to dilutions and concentrations is how we can determine concentrations using an analytical instrument. So the spectrophotometer, or often just the spectrometer, is something we call an analytical instrument. We have an entire year-long chemistry course, Chem 341 and Chem 441, dedicated to analytical chemistry. So upper division chemistry majors take this class. And for those of you that are chemistry majors, this is something that chemists do as a profession. They use these types of high-tech devices to determine concentrations of unknown material. For example, when you pick up like a box of cereal or a packet of, I don't even know, a candy bar or whatever, right? And you look at the nutritional information, do you know what I mean? That tells you how much sodium is in it, how much sugar is in it, etc. Okay? Some chemists had to use analytical instrumentation to figure out what those concentrations are. And here is how the spectrometer works. Okay, so you have what's called a cuvette. And a cuvette is just a fancy test tube. Okay, it's just a test tube that's often square, or I should say it's rectangular. So it's got this very regular geometry. So it has a specified width. That is typically 1 centimeter. It can be different, but almost all spectrometers have, it's a 1 centimeter thick cuvette, or 1 centimeter thick test tube. And you have some solution in there, okay? Now this solution has to be something that will absorb light. And we'll spend a lot of time talking about that later on in the semester. What molecules absorb light, what molecules don't absorb light. For now, we'll just say we have a colored solution, okay? And because it's colored, that means it's absorbing light, okay? And hopefully we'll be able to dive into this a little bit more in your virtual labs. And so what this instrument will do, it'll pass light through at intensity IN, and it's really bright. So the size of this arrow indicates that there's a lot of intensity of light passing through. And we should also note that this could be visible light, it could be ultraviolet light, it could even be infrared light, or it could even be X-ray, depending on what technique we're using. So in chemistry, more often than not, these are the common. UV vis is very common, but IR and X-ray, they are also common as well. Most of what you will be exposed to as a beginning level chemist is ultraviolet and visible light. But like I said, we can use infrared or we can use X-ray. We'll talk a lot more about those different flavors of light as we progress through the semester. And so what's going to happen now, the solution, depending on its concentration, will absorb some amount of this light. And so the instrument measures the intensity of light coming out. And of course, this is in reference to the intensity of light going in. So the very first thing you do is give it a blank measurement so you know how much intensity in there is. Then you put your solution and you see what the intensity out is, okay? And look, this ratio T, that's called the transmittance. And this transmittance is always less than 1, right? I out divided by I in, because I out is always less than I in. So the sample has absorbed some of that light, okay? Transmittance can be converted into absorbance by taking the negative logarithm of the transmittance. Okay? So absorbance and transmittance are kind of like equal and opposite, all right? So they both reflect the same thing, just one looks at how much light has been absorbed, in the case of the absorbance. The other measurement looks at how much light passes through, in the case of transmittance. Either works, but often in chemistry we use absorbance, and this is the very famous Beer's law equation. Oops, I'm going to erase that so I have room to write. Okay, so Beer's law is given by this equation here. So let's break it down. Okay, so this B, that's our path length, right? So often that's about 1 centimeter. This, recognize that? Brackets, concentration in molarity. Okay? In molarity. And this term's, this little e right here, that's what we call the molar absorptivity. And that has units of 1/centimeter per molarity. It's a crazy unit, but the idea of the unit of this is when you take the units of this, 1/centimeter per molarity, times the path length, centimeter, times the concentration, molarity, all of the units cancel because absorbance is unitless. It's an arbitrary, like, how much light did the sample absorb, okay? And so the way this Beer's law works, here is a graph of Beer's law. So here's the absorbance, A, versus the concentration, C. And what a chemist or a scientist would do would make several dilutions. So they might start, for example, with their stock solution way up here, right? Because if you follow this on the scale, the stock solution would have a very large concentration, and you would make serial dilutions. So in other words, you would dilute this thing over and over and over and over again, okay? And so each one of these data points represents a new solution that you would have made from the stock solution by continuing to dilute it over and over and over again, okay? And what you get is this beautiful straight line, the slope of which is equal to the molar absorptivity, okay? And so now then, if you have an unknown concentration, which I'll draw with a box, so now suppose we have an unknown sample, like maybe somebody gives us a, I don't know, a commercial product, and we want to know how much of this stuff is in it before I sell it to the public, all right? So I would make a stock solution of that thing. I would make these serial dilutions, and then my unknown sample I would compare. So my unknown sample, I would be able to measure the absorbance. I wouldn't know the concentration of my unknown sample, right? It wouldn't be told to me. However, I can put in the spectrometer. The spectrometer is going to tell me what the absorbance is. And then now I can follow on my graph and say, aha, now I know what the concentration of that unknown had to be, okay? So it's a pretty cool technique. I do this technique in my own research. I use IR. I use infrared light in my research to do spectrometry. And we have all kinds of flavors of spectrometers in the chemistry department. We unfortunately do not have an X-ray spectrometer. However, we do have several UV vis, infrared. We even have a type of spectrometer called NMR, which is nuclear magnetic resonance. And that's very cool. That is a giant, giant instrument. It's about as big as a VW, or it's about as big as a small car, I will say. But it's cool. We have an instrument like that students get access to using here on campus, okay? So the last thing I'll say now, just an activity, so if we can follow through. So let's suppose we have a green stock solution and we make several serial dilutions. So which one has the largest concentration? So hopefully you can see that C, it's like the darkest green color, right? So this would be the most dilute because, you know, maybe we've completely diluted it so you don't even see the green color anymore. That can happen. This would be the second most dilute, the third most dilute, and then this might be the most concentrated. Okay, so that's all I'm going to say for now about this video, folks. I will see you on the next one. Hasta luego.